Welcome. Welcome to our first of two lectures on optimization. I'm pretty excited about these two lectures because we're going to see a lot of really interesting real-life problems which we can attack using the calculus skills we've developed so far. You'll recall that we now know how to use derivatives, the first and the second derivative, to find maximum and minimum values of functions, to determine the shape of a graph of a function. Well, now these functions will turn out to be models of real-life situations. And we'll use calculus, these skills we've developed, to find the maximum value of this function or the minimum value of this function. These are called optimization problems. We will optimize the function. We've seen some of these examples earlier, actually. We've seen a very simple example, the pig pen problem, where we had a fixed area and we wanted to minimize the amount of fence around the pig pen. Or on the other side, we had a fixed perimeter, a fixed amount of fence, and we wanted to maximize the area. So we've seen some fairly simple problems involving maximization or minimization using calculus. Today we'll look at some slightly more complicated problems. These problems will take a little more time to do, and hence they'll be more interesting, I think. This is basically one of the real motivations for the development of calculus. Calculus came along because it was a useful tool for solving real-life engineering and scientific problems. Let me give you an example of that. You might remember that Kepler developed some laws about the motion of planets around the sun. He had three laws. One of them was to the effect that the planetary motion around the sun was an elliptical curve. Well, Kepler did all this through observation. He basically looked at the sky and wrote down where the planets were on any given time, and then thought about it and said, oh, I think the planets are moving in an elliptical pattern. So all his laws were basically based on observation. Well, then along comes Isaac Newton, and using the calculus, he was able to prove that Kepler's laws were indeed true. This is one of the first applications of calculus, actually, to verify mathematically that Kepler's laws were indeed true. A note on models, again, I've made this commentary before. The models we'll see are fairly simple compared to real-life models. And the reason is, of course, a real-life model would be much too complicated to develop in these lectures. That said, they'll be tough enough. I mean, they won't be totally trivial. And the techniques we use to analyze these models, to find the maximum and minimum values, are precisely the same skills you would use with a more complicated model. Good, so why don't we get going with an example. This first example I don't think is too overwhelming, and I think you can see that it's actually fairly realistic. Suppose you're a manufacturer and you want to design open boxes. By an open box, I mean it has a bottom and four sides, but it doesn't have a top. Okay, so you're designing boxes, and you want it to hold the maximum amount of volume. You want it to have a maximum amount of volume. And your restriction is you're only allowed to use 108 square inches of material. I picked that funny number 108 so some of the arithmetic will come out nicely. But you could apply this technique to any box problem having a fixed amount of surface area, a fixed amount of material, a fixed amount of cardboard making up the sides and the bottom, and then you try to maximize the volume. So what should the dimensions be of this box? Should it be really, really tall with a tiny little base? Or should it be with a giant base but not very high? It's not clear at all what the dimensions of this box should be in order that the volume be maximum. This kind of problem occurs a lot in calculus. A similar problem you could imagine is designing cans. Suppose you wanted to design a can and you had a fixed amount of metal. So you have the surface area around the can and you might have the bottom and the top. And suppose the amount of metal is fixed. What's the optimal size tin can? Should it be like a tuna can? In other words, not very high but kind of wide? Or should it be a tall, skinny can like tennis balls come in? Well, again, these kinds of problems all sort of have the same principles that we're looking at in our box problem. So let's get to work on this problem. Again, we have a box with a square base and an unknown height, and we want to maximize the volume, and we have a fixed amount of surface area. So I suggest in almost all of these problems, draw a picture and label the unknown quantities. So here you see a box, and I've labeled the base x by x because it's a square base. So the base is the same dimension, length times width. And I've labeled the height h. So these are the unknown dimensions we're trying to determine in order that the volume be a maximum. Good. Well, what is the volume of our box? Well, it's base times height, isn't it? So the volume is going to be the base, x squared, times the height, h. That's the function we want to maximize. We want to make that as big as possible. There's a problem with it. It's got two variables, doesn't it? X and h. And we don't know how to handle that situation with two variables. So what we're going to do is get rid of one of the variables. And how? Well, we have a restriction, don't we? They told us we only have a limited amount of surface area. So let's write down what the surface area is. And then that quantity equals 108, because that's the fixed amount of surface area. So how much surface area is there in a box? Well, the base is x by x, so x squared makes up the base. And how about the sides? There are 4 sides, and each has dimensions x by h. So the total surface area would be the base, x squared, plus 4xh, which is the sum of the 4 sides. And that has to be equal to 108. Good. So now we can use this restriction, this surface area restriction, to eliminate one of the variables. And I think it's pretty clear it would be easier to eliminate the variable h in this equation. So solve for h in the surface area equation, and you obtain that h is 108 minus x squared over 4x. Okay, you see how I did that? I moved the x squared to the other side, and then I divided the entire right-hand side by 4x. So now I know what h is in terms of x, and I can plug that quantity into h in the volume formula. So our volume formula becomes volume equals, well, it used to be x squared h, but now it's x squared times 108 minus x squared, all divided by 4x. Good. We now have a function, a volume function, involving a single variable, x. And what do we want to do? We want to maximize v. We want v to be as big as possible. So I'd like to find the high point on the graph of v, the maximum value. What are our skills that we use for this? Well, we take the derivative and set it equal to 0, don't we? And that would be the high point of the graph. Now, look at the formula for volume the way I've written it here. It's fairly unpleasant to differentiate that because it would require a product rule and a quotient rule. Ouch! So multiply through. Do some pre-processing before you differentiate. This is always a good skill to keep in mind, a sort of a study hint. When you're trying to differentiate something, look to see if you can simplify it first before you differentiate, because you might avoid ugly rules like the product rule or the quotient rule. So if I multiply the x squared into the parentheses, this simplifies to 27x minus x cubed over 4. And that's what I'm going to differentiate. But before I do it, I'd like to talk about the domain of this function v that represents the volume of my box. Well, of course, x had better be bigger than or equal to 0. In fact, you might argue that 0 is absurd, because if x is 0, there's no base at all, is there? But let's just assume it's on the closed interval starting at 0. Now, how big can x be? Well, I claim it can be as big as the square root of 108, because if you look back at the h formula, if x equals the square root of 108, then x squared is 108, and h turns out to be 0. So if x equals square root of 108, you have a degenerate box that has all of its surface area in the base, and it has no height. So we don't want that either. That box doesn't hold much. So x is in between 0 and the square root of 108. Okay, let's do some calculus now. Let's take the derivative. And that's sort of, as usual, that's the easiest step, isn't it? Isn't this curious? This setup was pretty tough going. We had to play with some equations and substitute values, et cetera, and now the calculus step is, boom, take a derivative. And the derivative would be 27 minus 3x squared over 4. That's the derivative of our volume function. Set it equal to 0 to find the critical numbers, and then you have to solve the equation 3x squared equals 108. I obtained that by multiplying through by 4 and then moving one term to the other side. And if you divide that equation by 3 and take the square root, you determine that x is equal to 6. Here's a little side comment. You might have wondered why I picked 108 as my fixed surface area. I did it so that the answer would come out to be nice, like 6. If you had picked, say, the surface area to be 100, then my answer would be some ugly number involving square roots, which is sort of unpleasant to deal with. So it turns out that x is 6. Now, is this a max or a min? Is this the maximum value or the minimum value? Well, there's a number of ways of checking this. Here's one way. We're defined on the closed interval 0 to square root 108. So there are only 3 possible extrema. The endpoints, the 2 endpoints, or this critical number here. Well, at the endpoints, the volume is 0. Those were the degenerate cases in which your box had no height or your box had no base. So the volume at x equals 6 is definitely going to be the largest value, and if you plug 6 back into the volume equation, you'll see that you get an answer of 108. Kind of a coincidence, isn't it, that the fixed surface area was 108 and the volume turns out to be also 108 cubic feet. Cubic inches, I guess we're using here. So 108 is the maximum value of this function, and then that's the base dimension. The other base dimension is also 6 because the base is square. And what's the height? Well, you would take x, plug it back into the equation for the height. So you plug 6 into that equation for h, and it comes out that h is 3. So our box is 6 by 6 by 3. Okay? Let me make some comments about this problem. We could have checked that this answer 6 was a maximum using some of the other tests we developed. We could have used the first derivative test by analyzing the sign of the first derivative on either side of 6. Perhaps even easier would be use the second derivative test. If you take the derivative, dv dx, and differentiate it again, you'll see that the second derivative is negative at 6. And that means that the curve is concave down It's concave down, so 6 is a maximum. Now let's be clear here. There are many, many boxes that have a surface area of 108 square inches. Lots of them. But the maximum volume is obtained by having the dimensions be 6 by 6 by 3. Here are some other pictures of boxes, all of which have surface area 108. You can check that. The surface area of each of these boxes is 108, but their volumes are less than 108. We found the optimal box, the one with the biggest volume with that restriction on surface area. Good. I hope you enjoyed that problem. Let's kind of extract some guidelines on how to attack these optimization problems. I highly recommend that the first thing you do, besides reading the problem, and it might take 2 or 3 times to read through it, is draw a picture. Label the quantities in your diagram, just like I did with the box. And then write down a primary equation of the quantity you want to maximize or minimize. Okay, and you may need some geometry for that. In the last problem, I needed to know the volume of a box. That was a geometric formula. You may need to know in a different example the volume of a cylinder because you're dealing with a tin can or something. And then you try to reduce this equation to an equation having just one variable. And the way you do that is you have some side restriction. Our side restriction last time was that we knew that the total surface area was 108. And so that let us get rid of the variable h, and we were left with a formula involving a single variable x. Then I recommend you determine the domain of the situation. Make sure you understand that there are restrictions on your variable x. Usually these come from physical restrictions. It's got to be a box with positive volume. Don't construct a box that has no volume. You can't ship much in such a box. And then finally, after all this is done, you bring in calculus. I mean, up to now we haven't used any calculus. Now you bring in calculus and you'll try to find the optimal answer using derivatives and analyzing the derivative and then making sure that you found the maximum using the first derivative test or the second derivative test or some of the other skills we've talked about. Good. Let's turn to a second problem. This is one of my favorite problems in optimization. I love this problem. It has a lot of really interesting outcomes, and I think you'll enjoy it too. It's a surprising problem. It's kind of tricky. The math that's embedded in this problem is a little messy, but not too bad. I think you'll be able to follow it just fine. Here's what's happening. Take a piece of wire. Let's call it 4 feet of wire. So it's about this long, 4 feet of wire. And what I do is I cut it somewhere, in the middle or halfway, someplace I cut it. And with one piece, I form a square. And with the other piece, I form a circle. So this piece of wire has been cut, a circle was formed, and a square was formed. And it's 4 feet of wire. Here's the question. Where should I make my cut on the wire such that the sum of the areas of the square plus the circle is a maximum? I want to maximize the total area formed by the circle and the square. For instance, I could not even cut the wire and form just a giant square. It would be 1 by 1 by 1 by 1, wouldn't it? Because I have 4 feet of wire, and each side would be 1 foot. Or, as another extreme, I could just form a circle with the entire wire and not have a square at all. Or I could cut it halfway, say, and make a square and a circle. I hope it's not clear what the answer is. Where should I cut the wire to maximize the sum of the areas of the circle and the square? Good. Here's a little picture of that. You can see the wire, and I've cut it somewhere in the middle and formed a square and a circle. I'm trying to find where to cut it. And there are lots of ways of labeling the unknowns here. I choose to do the following. Label the sides of the square x, and label the radius of the circle r. So I hope you can imagine that one piece of the wire is wrapped around to form that circle of radius r, and the other piece is bent to form the square of side x. Okay, so we have the situation. We have two unknowns. Let's now do some work. What's the area enclosed by those two figures? Well, the area enclosed by the square is, of course, x squared. That's the area of a square. And what's the area of our circle? Pi r squared. So you see, again, we need some pre-calculus geometry formulas here. Later on, you might see examples when you're doing our workbook, for example, that you might need the area of a more complicated figure, or the volume of a sphere, 4/3 pi r cubed. So these geometric formulas are always lurking in the background and have to be pulled in when you're doing applied math. So we also have a restriction on this situation. Thank goodness, because the area formula involves two variables, and I have to get rid of a variable. Well, what do we know? We had 4 feet of wire, and the square takes up 4x of those 4 feet because it's x by x by x by x. So 4 equals 4x plus, well, how much wire's in the circle? That's the circumference of a circle. That's 2 pi r. That's the formula for the circumference of a circle. And so I know that 4 equals 4x plus 2 pi r. And that's our secondary equation that will permit us to delete one of the variables in our area equation. I think it's better to delete r, and here's how we do it. We solve for r in our restriction. We get pi r equals 2 minus 2x, and that implies that r equals 2 minus 2x over pi. Okay, now take this radius and plug it into the area formula, and you get area equals x squared plus pi times our new value of r all squared. And then I'm going to simplify that slightly. The pi squared in the denominator can cancel with one of the pi's, or with the pi on the outside of the parentheses, and you're left with x squared plus 1 over pi, 2 minus 2x squared. Now I'm going to want to differentiate this to find the critical numbers. Again, I prefer to multiply it out. It'll be simpler to differentiate. Otherwise, I'll need the chain rule. So if I multiply it out, it's x squared plus 1 over pi, and then I square that term, and I get 4 minus 8x plus 4x squared. I think you see the domain is 0 to 1. If x is 0, then everything belongs in the circle, and if x is 1, everything belongs in the square. So those are the restrictions on x. Now, that was pretty tough, wasn't it? This is the hardest part of the problem, setting it up. All right, let's find the critical numbers. So we take the derivative of our area equation, and we get 2x plus 1 over pi times minus 8 plus 8x, and we set that equal to 0. The calculus part, in a sense, is over. We've taken the derivative. Now we have to solve for x, and that requires some algebra. Multiply through by pi, and you get 2 pi x minus 8 plus 8x equals 0. Factor out the 2 pi plus 8 times x equals 8. I've moved the 8 to the other side. Divide, and you finally get x equals 4 over pi plus 4, which is about 0.56 on your calculator. Now, a lot of students would do the following. They would circle this as the answer and say that's the value of x that maximizes the error. Maximizes the area of the two figures. Well, they'd be wrong. This is what makes this problem so interesting. Remember, maximum and minimum values can occur possibly at the endpoints. So not only do you have to evaluate the function at this critical number, but you've got to also check those endpoints. So if you take the area when x is 0, you get a number about 1.273. In other words, plug x equals 0 into the area equation. And if you plug the other endpoint, x equals 1, you get an area of 1. And if you plug in this critical number, the one in the middle, 0.56, if you plug that into the area equation, you get approximately 0.56. Trust me on that calculation. It's kind of a coincidence. You get the same answer back. So who's the winner here? Oh, 0 is the answer. X equals 0 will give the largest volume. What does that mean? Wait a minute. That means no square at all. This piece of wire should be used to form a circle and nothing else. And that will produce the maximum area. Isn't that curious? You know, it's kind of cool. If I had asked the question, where should I cut the wire to minimize the sum of the two areas, then that answer we just obtained, 0.56, would be correct. But I asked maximize, and the maximum area occurs at an endpoint. So what's the moral of the story here? Be careful. Your answer's not always going to be that critical number that you get by taking the derivative and setting it equal to 0. You've got to check those endpoints. You've got to be aware of your domain. Here's a graph of the area function of our wire. And you notice that the 0.56 value is actually a minimum. And the maximum occurs when x is 0. And over at x equals 1, it's not a max or a min. So it's kind of a curious problem, I thought. And it's a lot of fun to do. Now, students often come to me and say the following. Professor Edwards, why do we need calculus at all? Why can't I just set up the problem, say in the previous problem, form the area function, and then graph it, and use my calculator to find the minimum or the maximum? And I say, well, yeah, that may be true on some of these simple problems, but in real life, you can have some complicated models, and sometimes your calculator can fool you. So I'd like to invite you to try the following problem with your graphing utility. I made up a function that's kind of weird looking, but it's a function that fools graphing calculators. So it's kind of neat. Here's the function. It's f of x equals 1 minus the quantity x minus 1 squared minus a giant term, 1 divided by 1,000 times x minus 1 to the 1/7 plus 1. You might ask, how did I ever come up with this function? Well, it took some time. This is a very complicated function. Now, I'm going to graph this function on a standard viewing rectangle on a calculator. And it seems to me that the maximum occurs around x equals 1. And in fact, if you use the maximum button on your calculator, it will tell you that the maximum is 1 at 1. But wait, plug in 1 into this formula. What is f of 1? I'll step through it. It's 1 minus 0 minus 1 over 1. So f of 1 is 0. So the calculator gave a wrong answer. And visually, that's not what's really happening with this function. So you can be fooled by looking just at the calculator. We would need calculus to really solve this problem. Well, great. We've seen a couple of, I think, fairly interesting examples of optimization, and then a problem that kind of fools your calculator. So we can't just rely on calculators alone. We really do need calculus. Next time, we'll do some more, I think, pretty exciting applications. As I said, this is the heart of calculus. This is the core of applied mathematics, using calculus to solve engineering problems, building boxes, etc. These problems are sometimes difficult, and I think they're difficult for a couple of reasons. One is it requires reading a paragraph and setting up a model, and that can be hard. That usually requires a lot of geometry and pre-calculus. You need a lot of formulas. The calculus portion is often fairly straightforward. Do some derivatives, check your domain, etc. So next time we'll see some more examples, and I hope you enjoyed today's lecture. See you next time.